Hello everyone, this is Juan Freire and I have prepared a few slides to present contact graph based route determination procedures, what are current limitations and what are the ongoing discussions. This is relevant for the schedule aware bundle routing CCSDS whitebook development currently going on in the CCS community. So, current routing in ION works as follows. It assumes a contact graph structure of the network topology, where the different nodes are actually the contacts of the topology, and each contact has a start time and an end time, and there also happens between a source node and a destination node. And given this structure, the contact graph is formed given the origin, which is in this case node A, and the destination, which is the node D, and all the contacts that can lead from node A to node D in the topology. So CGR, which is the contact graph routing procedure implemented in ION, use a series of Dijkstra searches in this way. It begins a first search with the contact graph with every contact enabled in the contact graph, and use Dijkstra to find the shortest route to the destination, which in this case it's the red one. And then it stores this route in the route list structure, and to then suppress the limiting contact or the initial contact of this path out of the graph, to then repeat a second search without considering this contact. Therefore, the best route in this second search is going to be the cyan colored one, and this best route is then added to the route list, and the procedure repeats again, and the initial contact of this path is removed, and then in a third search there is another route that can be found towards the destination, and then this is also added to the route list structure. And then if we remove the initial contact of this route, then there is no more routes to find, and the search ends with 3 routes found toward the destination. Removing the initial contact of the contact graph of each route that were found allows to find different routes toward the destination. Then this route list that we can get out of this procedure is used for forwarding. So once that this procedure is executed, each node can use a list of this route to determine which one to use at a given moment when a bundle is ready to be forwarded. So this route list structure not only includes like the best delivery time to a given destination, but it also includes some other metrics which are relevant for the forwarding stage. One of them is eventually, obviously, the next hop, which is the identification of the next hop node that we need to use to get to a given destination D, and which is the starting time that route can be used. So, for instance, in this case, time 1000 is good to use the first route in the list, and then also each route has a due time, so it is a time that where the route is no longer valid, so because the route it's in the past already. So that route due value is very important as well in the route list. And there are other secondary metrics such as confidence or capacity, which can be relevant for forwarding. However, for instance, route capacity is no longer used in ION. It was originally used for determining whether if a bundle can fit in a route. However, that is no longer necessary if you use reactive fragmentation, where a bundle can actually be split in smaller packets and fit it in routes, even though the capacity of the route is smaller than the bundle size. Confidence is another metric which is under discussion at the moment, where you can actually use that parameter to decide if a bundle needs to be cloned or duplicated because it's being forwarded through a route which is not very reliable. And there's the correct usage of these values still under discussion. However, those metrics at the moment needs to be calculated from routing. So one consideration from the Dijkstra execution over a contact graph is the loop-free property of Dijkstra. By definition, Dijkstra is loop-free. You don't go back, you do not consider the same visited node And this is good, and this is something we do want out of contact graph. However, this loop-free property in a contact graph is not necessarily a loop-free property in the topology of the network. So let's consider this little example here where we have node A and several contacts toward destination D. And we have here contact 1, 2, and 4, and 5, which are very common situations when you use full duplex links, where you have a forward path to, for instance, in this case, from A to B, and then also you have a return path from B to A. So in this case, contact 1 eventually leads to contact 2, which is a return path toward the same destination A. So this can be a little tricky, because if we run a Dijkstra in this path, obviously a good solution would be this: from A, use contact 3, and then get to destination D, which will be a direct access from A to D, which is good. It has a best delivery time of 300, and that's right. However, another possibility, and this can also happen because Dijkstra is a cost-oriented algorithm and only wants to find a lowest cost route. There is another route with the same cost than this one, and it's a 300 best delivery time cost. And it's a route that goes through 1, 4, 5, 2, 3, and then D, which is also a valid path from a contact graph perspective. And it's also loop-free, even though there is not really a loop-free property of this path in a real network. So even though I do not visit 2 times the same contact, I do have a loop in the real topology. So if we have a look at how the real topology looks like, this path is goes to node B, then goes to node C, and then goes back to node B, and then to node A again, and then to node D again. So actually there is a loop in the real topology while there is not a loop in the contact graph. So the workaround for this is to track visited nodes during contact graph exploration, so which is some complexity that needs to be added to Dijkstra, and which is currently not taken into account at least in Ion implementation and many other implementation of these algorithms. The problem is that with the current formulation of Ion, of CGR in Ion, is the removal of the initial contact of each path can be a little bit problematic, because in particular in topology like this, where the first contact actually leads to many other contacts, and actually finding a best route through this contact does not really imply that we are finding all the route through that contact. So for example, in this topology where node A, for instance, which reach node B through contact number 1, can be a node which is on internet, which have a very, very long contact with node B, and this node B actually have a different set of contacts with node C, which can be a satellite, for instance, and have time-bounded contact with the node C. If we run the first Dijkstra search, we're going to find the single best route toward destination C, and then we will have to remove the contact, the initial contact of this route, and then we are going to leave behind 2 possible routes that were not calculated in this search. So what the original statement of the routing in a contact graph stated was to use an anchor mechanism, where if we have a node, a first node that is longer than the subsequent contacts, then we could anchor here in this node, and we do subsequent searches through this anchor node, which is good because it allows us to find different routes towards the destination that we were not able to find previously. However, the property of the anchor search is that the only anchor point can be the initial contact and not other ones. So this is a limitation we'll discuss a little bit further. And then when no more routes are found through an anchor contact, then the anchoring search ends and the search continues as originally stated. The problem with anchor contact is that it's not general enough. So node A can be another satellites, let's say, that have a lot of contact, a very long contact with a second satellite B, which in turns actually then have another contact with the node C in different times, like contact 2, 3, and 4 in this case. So in this case, we will anchor in the initial contact as well, which is contact number 5, and then we would look at the best route that we can get through number 5, which is the green one, However, after that, we will remove the initial contact of this route, and then there will still remain 2 routes without being found, even though we have used the anchor strategy in this situation. Another limitation is when another route is outside the anchor scope. It happens like this: we start anchoring on the initial contact, then we find the best route to C, which in this case has a best delivery time of 500, and then we do the second search, and however the second search finds that there is a route with a best delivery time of 600, which is like the next best route in this case. Since the route is not going through the anchor contact, then the anchoring strategy ends, and the anchor contact is then removed or suppressed from the contact graph, and there remains 2 routes that were not found with the anchor strategy. And there is a more general limitation, which has not necessarily to do with the anchor strategy, but however it has to do with their elimination or the suppression of the initial contact in the route. So let's consider this very simple topology from A to C, and then when we find the first route to C, which is through contact 1 and then contact number 2 with the best delivery time of 500, then we do remove the initial contact of this path. There is no anchoring here, no need for anchor. So we remove this contact, and then there is a second route that's still not being found. The anchor concept here is not necessary because the original contact, the initial contact of the path, is no longer than the second contact in the path. So there is not the limiting contact still being this one. So no anchoring can be applied in this scheme. So even though the limitation is not only on the anchor strategy in current CGR, but also in the removal and the suppression of the initial nodes in the path. So the thing is that the current issue of anchoring and the removal of the initial nodes in current CGR statement is that it's not able to find all routes in a contact graph. And this actually leads us to a more general question, which is, do we really want to find all these hidden routes behind in a contact graph? This is not an easy question. It's rather philosophical on the usage of schedule-aware boundary routing, and it has an importance because in the end the current forwarding only need the next contact. So we only want to know the next hop. We don't really want to know the complete path to our given destination. So there are possible answers for this question. So if we do want to find all routes, well, current CGR statement fails to do so. It's not accurate enough, so there needs some changes here. But however, if we do want to find all routes, then there is not really a need for Dijkstra. Dijkstra is an algorithm that's able to find the best route out of a graph. And if we do want to find all of them, then there is no need to find the best route. There is need to find all routes, and eventually out of these findings we can then sort with best delivery time, for instance. So actually greedy algorithms can be more efficient if you want to find every route in a path in a contact graph, because you don't need to run Dijkstra several times to find all the routes. So I'm going to show in the next slides a little bit more, a few results we are seeing with this one. But it is important to know that if we want to find all paths to our given destination in a graph, every one of them, then Dijkstra makes some sense. Dijkstra is good to find the best path in a graph. So, and let's say that no, we don't want to find all routes. Maybe some of them is good enough. Well, in that sense, our anchor search provides some good routes. However, there is no guarantee that they can be the best one, because this, as we explained in the previous limitation section, maybe some good routes are still being disregarded in the anchoring search. So if we do want to find only a few routes which are the best, then other formulations or the algorithms such as K shortest path algorithm are more efficient. And one implementation of this is called Jens algorithm, that you can provide a maximum number of best routes that you want to find in a given graph. This will be a more appropriate approach, and indeed this approach do use the Dijkstra because you need to get the best route out of a graph. So an interesting discussion about an implication of whether if we want to find all or some roots out of a graph is how accurately we can calculate an x-hop metric if we do not find all roots. Because if we want to get the next hop capacity, for instance, out of this simple topology, then there is no way to be exhaustive and accurate in the calculation of the capacity of a route of a path through a proximate node 1 in this case, if we do not find all the possible routes that go out that leaves that node toward the destination C in this case. So finding only a subset of the route in a graph can be counterproductive from the metric determination calculations. However, calculating all routes in a graph is very complex and do requires important processing resources. So this is probably the most interesting analysis to show here. And in this graph, we have used a benchmarking topology out of ring road network benchmark we've been using for a while already. It's a complex topology, and then even with very few contacts, where few means 530 contacts, leads to a lot of possible routes to different destinations, and the combinatorial effect of different combination of contacts is very big. So this is like quite a pessimistic scenario where we are testing CGR, which is the blue line, CGR with the anchoring mechanism and everything that's currently implemented in ION. And then we are using Yen's formulation to find a limitation to find 10 routes, 100 routes, and 1,000 routes, which are the best 10, 100, and 1,000 routes out of the contact graph. And then in the cyan colored curve, we are testing the depth first approach, which is a greedy algorithm that finds all routes in a contact graph. And these are the results. On the left, we have the runtime execution in seconds of this. These are preliminary implementations anyway, so these are just for reference. And these are executed on a desktop computer, so this is a good computer in processing capabilities. So, and we can see that CGR is quite bounded in the execution time, which is expected. I mean, it's like something we would expect, because CGR only finds a series of searches and then just remove the initial contacts, and if no more routes can be found, it just ends. And this can be also sustained by the curve in the right, where the quantity of route found for contact graph in this topology is only 1, even though we increase the number of contacts. And this is because of the issue that we've been seeing, that when a contact is behind a permanent contact without the anchoring, that cannot do the anchor effect. So you probably miss a lot of route finding from behind that contact. So this is a very pessimistic topology when this happens. And since CGR is only find one route, then it finds one. It just run one Dijkstra and then it ends. Therefore, the running time is always stable. However, only one route is found in this procedure. However, if we use Yen algorithm, then we see that for 10, 100, and 1,000 routes, we see that as we increase the number of contacts, and therefore we make the topology bigger and more complex, the calculation time increases just until the point the Yen algorithm is able to find the expected route. So, for instance, the violet curve, which finds 100 routes, when it reaches around the contact number 300 or something like that, a little less, maybe 270, then the route search remains pretty stable in the running time. Obviously it increases because the topology gets more complex and the Dijkstra searches are longer. However, it's bound. It doesn't increase so drastically as in the first part of the contact complexity increasing increment. So, However, we see that that as evidently as the quantity of root that we demand to the end to the k-shortest path algorithm, in this case implemented in a yen algorithm, before we reach that non-maximum quantity of root, the complexity and the processing time required for this algorithm is increased drastically, which is like the slope in the curve toward the left of the full graph. And then when the algorithm finds a stable root quantity, then it gets quite stable in the processing time. It doesn't increase it that much. However, if we see at the greedy algorithm, which is the latest curve below, it increases, it increased quite dramatically as well. However, not quite as dramatically as yen's in the beginning, but it's more dramatic after yen finds the required number of roots. This is a greedy algorithm that even though that the complexity of the topology increases a lot, its slope of running time increases constantly, and it is able to find a lot of roots and even more roots than the other algorithms. So whether if we choose to find all roots or we choose to find some of them, then there is a trade-off between a greedy algorithm and only an algorithm that's able to find a limited quantity of best root in a contact graph. So, well, this is just a general discussion. This is a preliminary analysis we're making, and I think this like a technological implication of whether if we choose to find all roots or some of them in a contact graph for scalable boundary routing. So, well, this is what I have to share, and this certainly opens discussions a little bit and suggests that further thinking needs to be done regarding what's the best way or what's the most efficient way to find the roots in a contact graph. So, well, anyway, you can write me or just contact me if you need to if you like to know some details. I will work a little bit in processing more of this information so we can better see why are this complexity happening, and however they are pretty reasonable in the sense that the greedy algorithm does not run any complex search. It's just explore the graph, and then this is escalation of runtime is quite logical. The yen algorithm is also logical because in the beginning it runs several Dijkstra. It increases as the contact increases, so that slope in the beginning is something that we could expect for, and well, CGR also is reasonable. So in the first place, this is intuitive and it seems to be right. But well, I think there's need some discussion ahead, and so well, we work on that. So well, thank you, and hope this helped somehow.